So we have Advanced Engineering Mathematics Practice Final Exam Part 1. Let's begin with number 1. Find the general solution near x equals 0 using the method of Frobenius. X squared y double prime plus x quantity 3 minus 2x y prime plus x squared minus 4 y equals 0. For part A, determine the indicial equation. Heard it pronounced both ways many times. Part B, determine two linearly independent solutions. Part C, determine the radius of convergence of the series. Okay, so this is a singular ordinary differential equation, ODE, and Frobenius method problem. So we're given that x squared y double prime plus x times the quantity 3 minus x times y prime plus quantity x squared minus 4 times y equals 0. So we're going to assume that y equals the sum from n equals 0 to infinity a sub n x to the n plus r, where a naught does not equal 0. So from there we could say that taking the derivative, y prime equals the sum from n equals 0 to infinity n plus r a sub n x to the n plus r minus 1. And then y double prime equals that sum here, and from n equals 0 to infinity, quantity m plus r times the quantity m plus r minus 1, a sub n times x to the n plus r minus 2. So from there what we could do is we could substitute x squared y double prime equals that sum, n plus r times the quantity n plus r minus 1, a sub n x to the n plus r. And then 3x y prime equals 3 times that sum, n equals 0 to infinity, n plus r times a sub n x to the n plus r. So negative 2x squared y prime equals negative 2 times that sum, again, n plus r a sub n x to the n plus r plus 1. So x squared y equals the sum, a sub n x to the n plus r plus 2. And negative 4y is going to equal negative 4 times that sum, a sub n x to the n plus r. So what we have here is that the lowest power is x to the r, and its coefficient gives the indicial equation or indicial equation r times the quantity r minus 1 plus 3r minus 4 equals 0. So r squared plus 2r minus 4 equals 0. And solving for r equals negative 1 plus or minus the square root of 5. Therefore, the two Frobenius exponents are going to be r sub 1 equals negative 1 plus the square root of 5, and r sub 2 equals negative 1 minus the square root of 5. And for k is greater than equal to 0. The recurrence is going to be this bracket, quantity k plus r squared plus 2 times quantity k plus r minus 4, close bracket, a sub k minus 2 times quantity k plus r minus 1, a sub k minus 1 plus a sub k minus 2 equals 0, where we have a sub negative 1 equals a sub negative 2 is equal to 0, and hence a sub k is going to equal the following: 2 times quantity k plus r minus 1, a sub k minus 1 minus a sub k minus 2 over the quantity k plus r squared plus 2 times the quantity k plus r minus 4. So from there, this is going to yield two independent solutions, which are going to be y sub 1 equals x to the negative 1 plus square root of 5 times the sum n equals infinity, n equals 0 to infinity, this a sub n 1 x sub n, and y sub 2 equals x to the negative 1 minus square root of 5, n equals 0 to infinity, a sub n superscript 2, or parentheses 2, x to the n. And this is also, these are read differently. These are just, I'm just reading as is for sake of brevity. And here, the only finite, we could conclude the only finite singular point of the differential equation is going to be x equals 0. And the Frobenius series has r equals infinity as its radius of convergence. So that's the overview of number 1. Some of the computation for the problems is left out just because this is more setup based. Okay, so building on that, let's go to number 2. Number 2, we want to consider the following nonlinear initial value problem. Okay, so dy dx equals, whoops, sorry about that. Let's see if this sticks. So dy dx equals y squared. Let me just put some tape on this. Sorry about that. Hold up. A little bit of humor this morning. So, okay, consider the nonlinear initial value problem dy dx equals y squared sine x plus x squared y with y of 0 equals 1. Use the Picard iteration to determine the first 3 successive approximations, then discuss local existence and uniqueness. Okay, so nonlinear differential equation. So the initial value problem IVP is y prime equals y squared sine x plus x squared y, where y of 0 equals 1. So the Picard iteration is y sub n plus 1 of x equals 1 plus this integral from 0 to x of bracket y sub n s squared sine s plus s squared y sub n of s close bracket ds. So we're going to begin with y naught of x equals 1. So then y sub 1 of x equals 1 plus the integral from 0 to x, quantity sine s plus s squared ds. Now from here, we could say y sub 1 of x equals 1 plus the quantity 1 minus cosine x plus x cubed over 3. So y sub 1 of x equals 2 minus cosine x plus x cubed over 3. So over here, we have y sub 2 of x equals 1 plus the integral from 0 to x, bracket quantity 2 minus cosine s plus s cubed over 3, close parentheses squared, sine s plus s squared parentheses 2 minus cosine x plus s cubed over 3, close parentheses, close bracket, ds. So this is a valid second Picard approximation. And the third approximation is y sub 3 of x equals 1 plus integral from 0 to x, bracket y sub 2 of s squared sine s plus s squared y sub 2 of s, close bracket, ds. And since f of xy equals y squared sine x plus x squared y, and the partial derivative of f with respect to y is going to be 2y sine x plus x squared, these are both arc continuous near 0, 1, then Picard-Lindelof theorem guarantees a unique local solution. Okay, so that's all for number 2. Moving along now to number 3. Let's see if this holds. Number 3, solve this. Y double prime plus 4y equals 3x, subject to y of 0 equals 1, y of pi over 2 equals 2. Determine whether the solution is unique. Okay, so this is a boundary value problem. We're going to solve for y double prime plus 4y equals 3x. So the homogeneous equation is y sub h double prime plus 4 y sub h equals 0. So y sub h equals c sub 1 cosine 2x plus c sub 2 sine of 2x. So we're going to try a particular solution, y sub p equals ax plus b. Then y sub p double prime equals 0. So we're going to get 4 times the quantity ax plus b equals 3x. So a is going to equal 3/4 and b is going to equal 0. Therefore, y is going to equal c sub 1 cosine 2x plus c sub 2 sine 2x plus 3/4 x. And if we use y of 0 equals 1, c sub 1 equals 1, and use y of pi over 2 equals 2, and y of pi over 2 is going to equal cosine pi plus c sub 2 sine pi plus 3/4 times pi over 2. So what we're going to get from there, negative 1 plus 3 pi over 8 equals 2. But This will require 3 pi over 8 equals 3, or pi equaling 8, which are both false. So what we could conclude is the boundary value problem has no solution, and so the solution is not merely non-unique. The solution itself, it does not exist. Okay, so that's all for part 1. Thank you very much and have a great day.